Okay, so I'm going to be talking about the next set of lab reports, but firstly again I will remind you that when you receive the question, look at the table and the units of the headings and the labels of the table, and those will give you an idea of what topic the practical is to do with. Then once you've managed to identify the topic, you should remember the formula required for that topic, and then be able to use those formulae in order to manipulate the data which she's given you. Okay, so the first one today was nuclear medicine, and as you can see here, so the purpose of this experiment was to measure the using a scintillator counter, basically the counts of all the pulses of a material. So the machine gives you a discriminator level in terms of 100, as you can see here, from 100 up to 900, but you must remember that the actual discrimination level you'll be using to plot the graphs is the discrimination level in volts. So as you can see here, per 200 discriminator level on the machine, a discrimination level of 1 volt is seen. So you can calculate those quite easily. Then these two sets of data are the ones which are recorded. So as I've said here, they will be the ones which will most likely be already provided to you. So that's the counts of the signal plus the noise, like the background counts as well. So that's the noise plus the signal. And then for each discriminator level, also they have different noise signals as well, which you also have to record. And if those are the ones you're recording, then, as I've mentioned here, you can then calculate the signal count without the noise, which would give the signal count itself. So as you can see from the equation here, the signal count is the signal plus noise count, which you first recorded, minus the noise count by itself. And as I've also stated here, although those are the most likely two sets of data to be given to you, they could give you two of these, and they might ask you to calculate the other, so you just have to rearrange this equation. So that's quite easy, as it's just adding if you bring the noise one over here, and etc. That was then used to form a signal versus noise ratio, which, as it's a ratio, all you have to do is take the signal value, the signal count, and divide that by the noise count. So you're basically just determining how much greater the signal count is than the noise count. So that's these values in the final column. Then you were asked to plot two graphs. So the first one was the discrimination level here in volts against the signal noise ratio. So that's this graph here. As you can tell from these two up here, they're most likely anomalies here. But the sole purpose of drawing this graph is to determine the optimum discriminatory level, or the discrimination level, which is the peak of the graph, basically. And then the second graph you were asked to draw, or you could be asked to draw, is simply the discrimination level against the signal count. And as you can see, that's almost perfectly linear. And the sole purpose of this graph is to just observe the pattern. So, as I've said here, it's negative correlation, or you'll have to say, as the discrimination level increases, the signal decreases. Okay, so moving on to the next one of light absorption. So in this experiment, you were shining different levels of wavelengths of light and looking at the absorption spectrum, or trying to draw absorption spectrums of the different wavelengths of light when the light was shone at a material. So this is the data, an example set of data, this table over here, and so this is the graph that has been plotted from this data, with, remember, the independent variable wavelength across the x here. So you're changing the wavelength of the light and observing the absorption of those different wavelengths of light. The purpose of this graph was to calculate the wavelength of light at which the most light is absorbed, which is called the lambda max here, so the maximum wavelength. And that would be the peak of the graph, which for you, as I've this arrow in red here and the number circled in red here, was 510 nanometer wavelength. As you can see just from the table, it has the highest absorption number. But as I've also stated up here, that technically if the graph was drawn more accurately, you can see that the line actually continues a bit further past 510 nanometers. So the peak wavelength may not necessarily be one of the wavelengths that you've actually measured. It could be between two, so around here somewhere. Then from this maximum wavelength, this lambda max, you could be asked to calculate the maximum excitation energy. So this is the energy of the light corresponding, or the energy of the photon that corresponds to that wavelength of light. So for this you need the equation E equals hc over lambda, whereby you have to substitute the maximum wavelength, so 510 nanometers, into that equation, remembering to put it in terms of meters, as that's the standard unit of wavelength. And also you have to remember that h is the Planck's constant, written here, and c is the speed of light, which is also a constant, written here. And once that's done, that will give you the maximum excitation energy in joules. However, if you're asked to then put this maximum excitation energy into electron volts, then you would just have to divide your answer by 1.6 times 10 to the minus 19, which is the charge of an electron, to give you the value in electron volts. Now, part of this investigation again was the second experiment, where you were asked to, you were changing the concentration of the material or the fluid, the solution that was absorbing the light, and the light you were shining on it was this maximum light. So you were shining a constant level of light, wavelength of light at different concentrations of a solution. So you use these concentrations here, and based on the file, again you were calculating the absorptions of the light and the amount of light absorbed depending on the concentration, and this graph plotted here, which gives a kind of rapid increase with concentration, which gradually levels off. And here you're meant to determine the unknown metal ion concentration from the graph. And to do this, I quote from the file, you have to draw two straight lines across the curve at the point of saturation. So this is where the curve begins to level off around here. You have to draw one from the origin up to that point and one down here. And the point of intersection, if you go down onto the x-axis from that point, that is the unknown metal ion concentration. So for this data, which is the same as the one you had in your report, that is around 2021 micromoles per litre. Then we can move on to the next one, which is skin impedance. So this is looking at a electrical impulse being sent through the skin, and you have to work out various things such as the impedance of the skin. Impedance is another way of saying resistance of the skin, as I've written down here. Resistance R equals impedance, which is the symbol Z, and as resistance equals potential difference over current, so does impedance, so Z equals U over I. You can then use this to plot a graph of the log of frequency as you were to retrieve the data of impedance, and you were taking the voltage across the electrodes when you were supplying a certain frequency through them onto the skin. That generated a current and a potential difference, obviously, and that was used to calculate the impedance. And so your graph is plotting, as you were changing the frequency across the electrodes, that on the x-axis, log of that against the log of the impedance. You were obviously using logs because there were large changes in the data, ranging from, like 20,000 down to 900, and all the way from 0 to 8,000 for the frequency. So logs allows you to fit the graph onto a better scale, basically. From this impedance of the skin, you can calculate something known as the specific resistance or resistivity of the skin, or of any material really. That symbol there is used, and that equals, so in this formula you have to remember the resistance or impedance multiplied by the area of the electrode used, so the area of the thing supplying the current. And for this, you have to remember the standard unit of area is meters squared. So it's unlikely that the electrodes will be a meter in size. And I think in yours there were millimeters. So remember to convert the dimensions from millimeters to meters before coming up with the final value in meters squared. Next, you should know that the capacitance, you have to know how to calculate the capacitance of the material, or the skin in this case. And so the capacitance with the letter, given the letter capital C, is calculated by dividing 1 by 2 pi multiplied by the frequency from the first independent variable of the experiment, multiplied by the impedance again. As I mentioned here, frequency in hertz, so they could give it to you in kilohertz or even smaller hertz, millihertz, so you'd have to scale that up to hertz again. And the unit of capacitance is known as the farad, so that's a unit you can't really work out just from this equation, so that's one you have to remember given the capital letter F. Speaking of units, the specific resistance one is not necessary to remember that it's specifically ohm meters squared, as you can work it out from the equation. As you're multiplying resistance, which has the unit ohm, by an area with unit meter squared, then you're obviously going to get a unit for the specific resistance of ohm times meter squared, or ohm meters squared. Finally, from the capacitance, you can calculate the specific capacitance given the symbol gamma, and this is calculated similarly to specific resistance by just dividing the capacitance by the area of the electrode, and this is a unit you can work out as well, based on the fact you remember the farad. So the unit would be farad divided by meter squared, farad per meter squared. So the next one is gamma absorption. In this experiment, pulses were recorded using a scintillation counter, similar to the nuclear medicine experiment, and you were measuring the count of a radiation source with a certain material placed in the way of the place between the source and the recording device. So you use lead, aluminium for example, and iron. And for this experiment, as you know, there is a background radiation naturally in the environment. So when you're recording the pulses, you have to be aware that the pulse recorded from the source will be inclusive of the background radiation as well. So you have to take account of these background pulses. So I've given an example here, just using one of the data points from your lab report. So if there's a pulse is recorded for lead with 5,610 counts, but you know there's a background count of 61.3, you can therefore calculate the count of the radiation source alone by subtracting the background radiation from the source plus background radiation technically, which you're initially recording, to get this value here. The next thing you had to do was to determine the half value thickness, which is the thickness of the material required to reduce the count to half its initial value, basically. A formula is given for this, so this is a formula you have to remember, which is the ln2, which you can remember is 0.693, and you have to divide that by the linear attenuation coefficient of the graph you plot for that specific material. This lab report seemed to be specific to lead. So for example, to find the half value thickness of lead, you would divide 0.693 by the linear attenuation coefficient found from the graph of lead. And the linear attenuation coefficient is known as mu on the graph, and so all the graphs will be in the form of y equals a certain value multiplied by e to the power of another value, which would be mu, multiplied by x, which is the distance. Next, similarly to the previous one, you can determine a 10th value thickness, which is the thickness required to decrease the initial count to a 10th of the initial count. So for example, decreasing 5,550-ish to 555. This has another formula to work it out, which is multiplying the half value thickness by 3.33. That's only an approximation, but it is the formula given. Last but not least, the mass attenuation coefficient can be calculated. This is calculated by dividing the linear attenuation coefficient by the known density of the material you're using. So this means you must be provided with the density of the material, or if they give you the linear attenuation coefficient and the mass attenuation coefficient, then they may ask you to work backwards to work out the density of the material and then possibly identify the material. So they could say a mass attenuation coefficient of a material of a certain number was recorded and put it in a graph with linear attenuation coefficient, so mu, of another value. What is the material? That could be the question. So you'd rearrange this, do the mass attenuation coefficient divided by the linear attenuation coefficient divided by the mass attenuation coefficient would give you the density, and maybe they would have a reference table with different densities in it, and you'd see which one that's the same as, and then say therefore the material is aluminium, for example. And from this mass attenuation coefficient you can determine a half value mass known as dm, and this is done by dividing ln2, or 0.693 again, by the mass attenuation coefficient you previously calculated to give you mu m, the mass attenuation, by dividing dm ln 2 by mu m to give you dm, the half value mass, which is the mass of material you required to half the count of the radiation source.